Formation of molecular orbitals. Now we know we were able to find out the shapes and the orientations of the atomic orbitals in the atom's model as per the quantum mechanical model of the atom on the basis of the Schrodinger's wave equation, which was, when solved, we got the three answers which are called quantum numbers. Now those quantum numbers gave us the shapes and the orientations of the atomic orbitals, and on the basis of which we were able to draw the atomic orbitals. Now we have to apply the same thing in case of the molecules. The difference is now the system is not monocentric, it's polycentric. Now if we want to find out, like suppose these are the two atoms which are overlapping, we are combining, and this is how they combine. Now what will be the shape of, this is their atomic orbital, this is their atomic orbital. What is the shape of the molecular orbital which is formed by the combination of these two atoms? We can't draw any structure. If you want to know the structure, if we want to know the shape of the molecular orbital, we need to know again the quantum numbers. Now this time these quantum numbers will be belonging to what? A molecular species, like the usual the atoms are having. Now in order to have the quantum numbers of the molecules for the electrons, to have the quantum numbers of the electrons in case of a molecular species, we need to know the equation of the electron in a molecular species in a polycentric system. Now the problem is this: we have been able to write down the equation for an electron in a polycentric system, but we have not been able to solve it. So that's why we don't know the exact answers of it. So we don't know exactly where, we don't know the quantum numbers of an electron in a polycentric system. So we can't draw its structure, the shape and the orientations. So therefore, we use as an approximate method to find out, to explain the formation of the molecular orbitals, which is called LCAO, and it's called linear combination of atomic orbitals. So LCAO is nothing but it's a linear combination of atomic orbitals. It works on the same principle as we have been using in order to explain the hybrid orbitals. What does it say? It puts three conditions for the formation of conditions for the formation of molecular orbitals. First condition is the atomic orbitals must have comparable energies, comparable or similar symmetry, and last but not the least, the overlapping must be maximum so that a very strong bond is formed. So on the basis of these conditions, LCO explains how atomic orbitals combines to form a molecular orbitals. Now let us see how this LCO explains this. Now according to this LCO, like let us take the case of a 1s combining with another 1s. When we say this is 1s and we say it's combining with another 1s, we know two types of molecular orbitals are formed. One is called bonding molecular orbital, other is called anti-bonding molecular orbital. Now, bonding molecular orbitals are formed by the constructive overlapping, whereas anti-bonding are formed by the subtractive overlapping. How does this constructive overlapping takes place? If suppose psi A is the wave function of the atomic orbital in the atom A, this is atom B, and psi B is the wave function of the electron in the atom B, then this psi dash is the psi is the wave function of the electron in the molecular orbital. It is the combination of the wave functions of electron in of the A and of the B. Whereas what is subtractive is, if psi dash is the wave function of the electron in the anti-bonding molecular orbital, it is actually psi A minus psi B, because it is the subtraction of the wave functions of the electrons of the atom A and B, as it is formed by the subtractive overlapping. So this is formed by constructive overlapping, this is formed by subtractive overlapping. Now let us see their shapes. Let us see now the formation of the molecular orbitals as per LCAO. Let's take the first example of a combination of a 1s with 1s. Now 1s orbitals are spherical atomic orbitals. When they overlap or combine with each other, they form two types of molecular orbitals. One is called bonding molecular orbital and another one is called anti-bonding molecular orbital. Bonding is formed by the constructive overlapping, anti-bonding is formed by the subtractive overlapping. Now what is another important thing is, when these two atomic orbitals combines and they have a constructive overlapping, their shapes changes from spherical to elliptical, and their bigger lobes are towards each other. Maximum electron density is now between them, between the nuclei of the two combining atoms, and that's why the extent of overlapping is maximum. Now, since the electron density of these combining atomic orbitals are along the internuclear axis, the bond formed is called sigma. And since it's a combination of 1s and 1s, we call it sigma 1s. In a very similar way. Again, the nucleus of these two atomic orbitals are in the same internuclear axis, along the internuclear axis, but whenever these two atomic orbitals combines, there is an equal possibility that they also forms an anti-bonding molecular orbital, in which subtractive overlapping takes place. Now you can see that no portion of any of the atomic orbitals is overlapping with each other, rather their bigger lobes are away from each other, which shows the repulsion between them. And that's why what we do is, we can show it in some way like this. If this is positive, negative, this is positive, negative. What we can show is, it becomes what? Almost positive, negative. But in this case, it becomes positive, negative, negative, positive, negative. It becomes opposite. This is how we can show. Now, this molecular orbitals is showing that there is no overlapping of the atomic orbitals. So that's why the energy is not becoming lesser. That's why this is drawn at a lower level than the atomic orbital, because the energy of the bonding molecular orbital is lesser, lower than the respective atomic orbital, whereas the energy of the anti-bonding molecular orbitals are higher than the combining atomic orbital. So it's drawn a little bit higher than this one. Now what we call these molecular orbitals? We call them sigma star 1s, because they are the anti-bonding molecular orbital of the same sigma 1s. And anti-bonding is designated by putting up a star as a superscript to the sigma. And 1s is written in the subscript because it is formed by the combination of 1s and 1s. We can say it has a one nodal plane where the possibility of finding the electron is probability of finding the electron is 0. So whenever the overlapping takes place, it's constructive overlapping, it's bonding molecular orbital. No overlapping takes place, subtractive overlapping, it's anti-bonding molecular orbital, whose shapes are like this. We call this as sigma 1s, we call this as sigma star 1s. Similarly, if 2s combines, we will be having sigma 2s, sigma star 2s. If 3s is combining, we will be having sigma 3s, sigma star 3s. And energy wise, they will be arranged in this way only. In the energy level diagrams, we draw these molecular orbitals in a very different way. That I will explain it to you later on. Now let us see the combination of a pz with pz. See, since we don't have a combination or those molecular species which are heteronuclear diatomic molecular species, we have only homonuclear diatomic molecular species. So we'll be only dealing with the overlapping of S with S, Px with Px, Py with Py, and Pz with Pz. So let us see the overlapping of 2Pz with 2Pz. Now 2Pz, 2Pz, they can show overlapping in two ways. It is almost as like this. This is 1 2Pz combining with another 2Pz. Now what we can show is, if their positive signs are towards each other, we call this as a constructive overlapping. This will result in the formation of bonding molecular orbital, and the shape of the bonding molecular orbital will be like this. What we find is the central lobe will be positive, negative, and negative. The two molecular orbitals are formed. Each one of these were having almost a shape like this. One lobe was bigger, the other one was smaller. Bigger lobes were towards each other so that they have a maximum overlapping, and the smaller lobes were on the opposite sides. Now, since the electron densities are along the internuclear axis in these combining atomic orbitals, the bond formed by these are called sigma 2pz. Sigma indicates the type of the bond, 2pz indicates it's formed by the overlapping or mixing of the 2pz atomic orbitals. So this is the shape of the sigma bonding molecular 2pz molecular orbital. Then there is another possibility that they may combine like this. In this case, positive, negative, it has negative, positive. We say they are not in the same with the same signs, they are not in the same phase, so they will have a subtractive overlapping. As a result, what we will find is they will form anti-bonding molecular orbital. The shape of this anti-bonding molecular orbital will be almost like this. Now the bigger lobes are on the other sides, smaller lobes are towards each other, and what we find is the charges are plus, minus, minus, plus. So almost no extent of overlapping. This red line indicates a nodal plane where the possibility of finding the electron is 0, and we will call these as sigma star. Star indicates antibonding. Sigma star antibonding molecular orbital formed by the overlapping or mixing up of 2pz. So these two are formed. Definitely the energy of this will be lower, the energy of this will be higher, and this will be present at lower energy level, this will be present at a higher energy level. Now let us see the formation of the 2px, 2px or 2py, 2py. Both of these will be almost of the same type. Let us see the formation of the 2px, 2px, and let us see how these 2px, 2ps overlap and what type of molecular orbitals they form. 2px are the 2px or 2py, it can be the same thing because they both will be having same type of overlapping. Now, it can be like this, where what we find is, if the signs are like this, we say they are not in the same phase. So we say subtractive overlapping takes place, and this results in the formation of an atomic orbital which is called anti-bonding molecular orbital, which is drawn like this, plus, minus, minus, plus. So this is your anti-bonding molecular orbital. We call this anti-bonding molecular orbital as pi. Remember, because the combining atomic orbitals electron densities are not lying along the internuclear axis. So the type of bond formed by them will be pi bond. So that's why it's a pi bond forming our molecular orbitals. But since it's an anti-bonding, we call it pi star. And since it is formed by the combination or mixing up of the 2px atomic orbitals, we call it pi star 2px. Now let us see how their constructive overlapping takes place. If they are coming like this and they have a same signs on the same side, we call it they are in the same phase. We call they will be having a subtractive overlapping, which will result in the formation of bonding molecular orbital, whose almost the shape will be like this. In this case, what we find is this becomes positive, this becomes negative. We can draw them like this also. This will be plus, this will be minus. Now, what we find is, now they are having what? Overlapping sideway. So they will be forming what? Which bond? Pi bond, because electron densities are not along the internuclear axis. And since it is a formation of formed by the overlapping or mixing up of 2px orbitals, we call it pi 2px. The same type of shapes will be shown by the 2py and 2py combination. So these are the typical shapes, and this is how these molecular orbitals are formed, which is explained as per the LCAO. Now let us see how we use these molecular orbitals in explaining the formation of the homonuclear diatomic molecular species. But before this, we need to understand the MOD explains not only the formation of the molecular species, it explains the bond order, bond length, bond strength, magnetic behavior of the molecular species also.